In classwork 5, we will be discussing transformations. Transformations are changes done to your core graphs. There are basically 4, or a fifth one we'll add, to your core graphs, or we can also call them parent graphs. So just so we know what we're talking about, we'll go through each one of them together. Absolute value functions, the core graph, looks like your basic V. This is written f of x, an absolute value of x. This is the parent graph for your absolute value function. Notice that the domain is all real numbers, and the range is from 0 to infinity. Next, we have a squaring function. This is your basic parabola, your quadratic, in which we have your parent squaring function. F of x is equal to x squared. The attributes for this are very similar to the absolute value one. Your domain, again, consists of all real numbers, and your range from 0 to infinity. Next, we have a square root function. Your square root function says f of x is equal to the square root of x. Remember how this gives us a domain restriction. So if we were looking to build our domain, we would be saying x has to be greater than or equal to 0. So the domain is from 0 to infinity. Let's take a look at your squaring function. It goes like this, like an arm. Your range can never be negatives, so therefore it is also 0 to infinity. The cubing function, we've been working with your cubing function, x cubed, and your cubing function looks like this. Again, its domain is all real numbers, and its range is also all real numbers. And last, we have the rational function. Now this we started to take a look at in our domain restrictions when we have a fraction, because in a denominator, this denominator cannot be equal to 0. So we took the 0 out of your number line, and we would have a domain of negative infinity to 0 and 0 to infinity. Because we take the 0 out, if you think about this, we will never be able to get a y value of 0 either, that this will return us a 0. There is nothing we can put in for x that would give us a y of 0. So therefore our range is also going to be the same thing. In this rational function, your x and your y-axis are actually natural asymptotes, and your function will go like this. Here are some basic transformation steps for vertical and horizontal shifts. These are actually translations. They are slides, and we've looked at a few of these before. In the f of x plus c, very similar to your x squared plus 1, and many of you already knew that was your parabola that shifted up 1. This plus c gives us a vertical shift up 1 unit. If something changes vertically, then our range is going to change. And by the same reasoning, a minus c will shift you down c units. Another one we use is when it's inside the parentheses, such as x plus 1 squared. When it's inside this parentheses, it's a horizontal shift. And the thing with these guys is they go the opposite direction. If it's a minus, it will go to the right. If it's a plus, it will go to the left. So your horizontal shift will affect your domain. So let's take a look at this example. Here's your parent graph. Your parent graph starts with, we'll call it another function name, x squared. So we start with x squared. Then we take this and we perform this transformation, plus 2. This shifts everything up 2 units. So we have a vertical shift up 2 units. This will change the range, where before the range for this was 0 to infinity. If we add 2, our new range for this is 2 to infinity. Here is an example of a horizontal shift. Your parent function, again, is x squared. So we start off with our graph with a parent function of x squared. We perform the transformation 2 units horizontally, and remember it moves in the opposite direction. We move 2 units to the left. And here is our transformed graph. This took a horizontal shift, two units left. This would change the domain, but since the domain was already all real numbers, it will stay all real numbers, and the range will stay at 0 to infinity. Here we have 2 basic rules of reflection. And when it's next to the x, if you think about it, on your grid, if x goes from a positive to a negative, there's a reflection in the y-axis. If y goes from positive to a negative, it's a reflection in your x-axis. So that's how the rule for this one is the x stays the same and the y negates. The rule for this one is the x negates and the y stays the same. So in looking at this, our parent graph is a square root function. Our parent graph goes like this. Here's your arm for your square root. For our transformation, the x is going to stay the same and the y is going to negate, so it's going to be a reflection in our x-axis. Our domain will stay the same, all real numbers. Oh, sorry, not all real numbers. Domain from 0 to infinity. And your range will now flip because you reflected this over the x-axis. So now we will be negative infinity to 0. The last part are our non-rigid transformations. These are like our dilations. But in this dilation, because it's on a graph, it doesn't change the x. It will only change the y values for these. And if you take a look at where we position C, if C is greater than 1, that means we have a vertical stretch. If C, this will be where your fraction is. What this does is this changes the distance to the origin. So for instance, in this one here, we have y is equal to 3 absolute value of x. We start with your absolute value graph. This is your core graph. And we do a transformation for a dilation of 3. What this does is this. If you have this point on your original 1, and this point was 1, 1, by multiplying it by 3, the x stays the same, but the y will go to 3. So this point will now be up here. So this is making this stretch in your function. This is called a vertical stretch. If I put a 1/2 out here, and I did the same thing and put the x of 1, y would give me 1/2. That would cause me to come out here. And I would be a shrink. Even though it looks flatter, it shrunk the distance to 0. So we're looking at the change in y's when we refer to this. Another way sometimes you see it is inside here, and you might refer to it as a horizontal stretch or shrink. It actually works the opposite of the vertical one, but has the same effect. You also always want to tell us that we have a multiple by a factor of, here's our factor of 1/2. This one was by a factor of 3. So these are our transformations.